Hello. Once again, you are welcome to today's lesson. Today's lesson is going to be lesson 2, okay, on the topic rational functions and partial fractions. Okay, in lesson 1, we looked at the definition of rational functions, okay, and we also looked at, okay, the definition of proper fractions, okay, and improper rational functions. So how to distinguish between these two, okay, proper rational functions and improper rational functions. Then, okay, mainly we looked at how to write the partial fraction identities. But the partial fraction identities, okay, we divided that into parts. We did the type 1, okay, then type 2. Today we are going to look at what's type 3. Okay, type 1, we looked at a situation where you have linear, okay, factors. Okay, linear factors. Type 2, we looked at a situation where we have quadratic what factors. Okay, whether the quadratic factors, okay, or the quadratic factor is factorable or not. Okay, so if it is factorable, then it will take out back to, okay, type 1. But if it's not factorable, then it means we know each fraction, the denominator will be quadratic, but the numerator will be linear. So today we are going to look at what the type 3, okay, which is a situation where you have your denominator with repeated what factors. So quickly, let me read what we have here. So when the denominator contains a non-factorable, so take note of this, repeated factors of the form as plus b all to the power n. And here, the n will not be 1. So the n must be greater than, okay, 1. Or it should be greater than or equal to 2. Because when you talk about repeated, then it means it is multiplying itself at least twice. So that you get, if it is x, it will be x times x, which is s squared, s times s times s, s cubed. So the least power here will be what? Will be 2. So that we can get repeated factors. Other than that, if it is 1, then it's just a factor, which is not repeated. I guess my point is well made. Okay, and now if you look at what we have in bracket, you can see that I have zoomed in on my repeated factor being linear. Okay, it's not strictly linear, it could be quadratic as well, only that still quadratic non-factorable. But if you get, okay, it's from the point of linear, by extension, you should get that of what the quadratic. So where a is not equal to 0, obviously, if a is equal to 0, this is it to be linear. Then the partial fraction identities will be of the form. Okay, so this is what we have here. Remember, it is your denominator that will tell you how your fraction is going to be, the nature of your fraction. Okay, so take note. However, before I come to this, okay, I'm going to take you from the known, okay, to the unknown. Okay, so assuming that maybe you have 1 over x, okay, then plus 1 over s squared. If you are writing this as a single fraction, what do you think your denominator will be?
X squared.
It will be s squared. Perfect. So your denominator will be s squared. Okay, so we are writing this indirectly as a single fraction. Okay, sort of. So s will go here. Okay, I mean s times that times this, so you get x plus, okay, this will go here 1 times this, so that will give us 1. So indirectly, okay, what we've written here is a single fraction of this partial fraction. Is that clear?
Yes.
So, okay, obviously. So this is fractions in parts, so partial fraction. Immediately you write it as a single fraction, obviously it becomes that your rational function that you are. So we are trying to say that this will be the partial fraction form of, okay, the single fraction that we have here. And you can see that if I had given you, okay, x plus 1 over s squared, okay, you can see that this time around your denominator here is a repeated factor. Okay, and that factor is x. Do you agree? Hello, do you agree? Okay,
So
so
please come again.
okay, so I said
Yes.
anytime, remember I said if you see s squared, what is the meaning of s squared? What is the meaning of S squared? It's
X
X
times
times X. Okay, which is the same as what? Okay, X being repeated. Is my
Yes,
point well
please.
made? So this is a factor. Anytime, so I can write this as X times X. Okay, so this is a repeated factor. I can write this as S times X times X, which is the S cube. So this is a repeated factor. However, your factor is repeated 3 times. Is that clear? Okay, so take note. You can see that the power here, okay, which is the power of your repeated factor, okay, indirectly will give you a rough idea, okay, of the number of what fractions that you can get from that repeated factor. Okay, so let me see. Obviously, if you want to get, okay, the number of fractions that your repeated factor can give you, then you have to depend on the number of factors that your repeated factor possibly can have. So if I have, okay, S squared, I know that the factors, one of them will be X and the other will be what? X squared. Am I right? Because we know every number is a factor of itself. Is that clear?
Yes, please.
Do you agree that this will be the set of factors, okay, when I'm considering what? S squared?
Yes,
Okay,
yes.
so what about if I'm dealing with S cube? The first one will be X. X is a factor of S cube. Do you agree?
Yes, sir.
Okay, then
Yes,
what
please.
else? S squared is a factor of S cube. Very good. Then
Yes,
also
please.
S cube is a
S
factor
cube.
of itself.
Yes, please.
Okay, so if you have S to the power 4, obviously it will be X, S squared, S cube, S to the power 4.
Yes.
Very good. So once you understand this, then the work is going to be easy for me in terms of explaining this concept. Okay, so you realize that the number of factors, so here, if it is S cube, we'll get 3 factors. So each of the factors that you have there will give you a fraction. So the number of factors possibly that you can get from your repeated factor will give you, okay, a fraction, will determine the number of fraction that you can have. So if your repeated factor is, okay, the power is 2, it means you are going to get 2 fractions. If your repeated factor, the power is 3, it means the maximum number of fractions that you can get will be 3. If the power is 4, the number of fractions maximum you can get is what? Is 4. Is my point well made now?
Yes, please.
Okay, so that's the more reason why. So it means if the power is 2, the number of factors will be 3. Will be, the number of fractions will be 2. If the power of X is 3, that's your factor. Okay, is 3. The number of fractions that you can get will be what? Will be 3. So 4. So if the power is N, how many fractions can you get? If the power is N, remember, if it is 2 fractions. If it's 3 fractions. If it is 4 fractions. So if it is N, how many fractions?
N fractions.
N fractions. So you can see that that's what you have. Okay, and obviously you will see, just as we did here, the first, okay, the denominator, your repeater, the first fraction, the denominator will be your first factor of this. And the first factor is always this, your linear factor to the power 1. Okay, just as you can see, the second one will be your linear factor squared. The third one will be cubed up towards the power of what you have here. So the first factor will be AS plus B. That is the denominator of the first fraction. The second factor, which is AS plus B squared, okay, will be the denominator of your second fraction. The third one will be AS plus B cubed. So you keep on increasing your exponent of this. So you get to what? N. So it means here I have N number of what? Fractions. Okay, the first fraction, the second, the third. Okay, then you can see plus ellipses. So I have a number of fractions between them, then plus my last what? Okay, fraction, which will be my linear, okay, factor to the power what? N. Is my point well made?
Yes,
Yes, sir.
Okay, very good. I've told you this is key. How you can get the partial fraction is key, because before you resolve, you have to write the partial fraction. So I'll take all my time to explain the partial fraction. And you should also make sure that you understand, other than that your future will be bleak. Okay, so at this point, let's look at this illustrative example. Okay, in actual fact, it should have been examples. Okay, so I will edit it because I have more than one. Okay, so if I have 3 over x plus 1 squared, you can see that this is a linear factor and it's repeated. Am I right?
Yes, please.
Okay, so once it's repeated, the power of what? Your linear factor here is 2. So how many fractions are we going to get?
2.
2. Okay, so in this case, you know the first fraction, the denominator will be s plus 1. The second fraction, the denominator will be s plus 1 squared. And you cannot go beyond squared, so you end there. The maximum that you can go is the power of what? Of your what you have there. Okay, so it means we can say that this is identical to, because the denominator is linear, the numerator will be a constant. Because the denominator, your repeated factor is linear, the numerator will be a constant as well. So if your denominator here was a quadratic which is not factorable, okay, then in each of the denominators, okay, we are going to get what? That's non-factorable quadratic with a power 1, power 2, okay, power 3. Let's say if this was quadratic, then it means the power will be 2. We are going to end here, maybe, assuming maybe I have s squared, okay, plus 1 all squared. Okay, you can see that if this is my denominator, let me use maybe 4x. Okay, this will be identical to, we cannot factorize this. S squared plus 1 is a quadratic expression but not factorable. So, but because the non-factorable, okay, I think I have this here. So when you get here, I will explain. Okay, so if you get this one, then I can move on. Is this one okay? The explanation to this one. Okay, so then if you come to this one too, okay, it's linear. Obviously, I didn't test whether it is proper or improper because, okay, we know that this will be proper. Okay, the degree here is 0. The degree here will be, this is repeated, so it will be x plus 1, s plus 1. So the degree will be 2 here. Okay, the degree here is 1. The degree of the denominator will be 3. Okay, so all of them will be proper. So now I can write the identity. So here I have 3s plus 1, linear repeated 3 times. So it means I will get 3 fractions. The first fraction, the denominator is known. The denominator of all your fractions will be known. So your first fraction, denominator will be your linear factor to the power 1. But I won't write it. It's simply understood to be there. The second one will be your linear factor. You increase the exponent by 1 squared. The third fraction will be exactly what you have, the cube. Now, because this is linear, your repeated factor is linear. In the numerators, each of them will be constants. Okay, so now let's come to this and see. I'm going to that one, I'll write it. Okay, let's see whether you get the concept, exactly what I want to write. Okay, so let's see. With this one, how many, let's see, is this factorable? S squared plus 1. If it was minus 1, they will know that it's factorable. But plus 1, we don't have sum of 2 squares factorization. We only have difference of 2 squares factorization. I hope you get the point. So we can't factorize. So this is a quadratic non-factorable. But we know that, okay, the power will tell us, okay, the repeated factor, the power, will tell us the number of fractions. So how many fractions are we going to get? Maximum. 3, is that not it? Okay, so if for nothing at all, I know that I'm going to get 1 fraction plus another fraction, okay, plus another fraction, all correct?
Yes.
Okay, now each of the fractions, I should know the denominators. And because it's a quadratic denominator, repeated, I will start from the s squared plus 1. Okay, the denominator here will be s squared plus 1 but squared. Is that clear? The next one will be s squared plus 1, then cube. Okay, because s squared plus 1 is a factor of this. S squared plus 1 all squared is also a factor of this. Then this is also a factor of itself. But because my denominator is what? Quadratic. Remember what I told you. Okay, quadratic, if you go above, it will be linear. So it means my numerator should be what? Linear. So this will give me ax, okay, plus b. Okay, this one too, repeated factor, okay, so quadratic. Numerator should be linear. Sorry, yes, linear, which will give you, you've used a and b. So it will be cx plus d. Okay, then this one will be E, okay, X, okay, plus F. Is my point well made, or I should come again?
Yes, please.
Which is it come
Please
again
come
or
again.
well made? Okay,
Please
Prophet,
come again.
okay, I'll come again. Prophet Ray, for your hand is up. No, it seems your line is bad. Please disconnect and reconnect. Prophet Refua, please disconnect and reconnect. Your line is bad. Prophet Refua, your line is very bad. Disconnect and reconnect. Okay. All right. Okay, so now I think, okay, you said I should come again, so I'm going to come again. Okay, as for your denominators, it shouldn't be any problem. I've told you, okay, I've told you this is what we have. Okay, so you have a repeated factor. Once you see a factor to a certain power more than one, other than one, okay, then it means we are dealing with what? A repeated factor. So this is giving you a repeated factor. So that factor that is repeated is s squared plus 1. And that s squared plus 1 is a quadratic factor. But this quadratic factor is not factorable. So you have a repeated non-factorable factor. So non-factorable repeated factor. Okay, so that's what you have here. So once you have that situation, then we are going to use the powers here, or the power. Okay, the number of times your factor is repeated will determine the number of, or tell you the number of fractions possibly you can get from that what rational function. So we said we are going to get 3 fractions because the power is 3. So my first fraction, my second fraction, my third fraction. If for nothing at all, my denominator fractions, I should know, okay, my denominators of the fractions, I should say. Okay, I should know each of them. The first one, remember we said when we had x, okay, I think it's here. When we had s cubed, we started with x, s squared, then s cubed. So our quantity that is raised to the power, we start with that one, then we keep on increasing the powers till we get to the power, okay, that your quantity comes with. That's where you stop. Because x, if you take it to the power 4 can never be a factor of this. Okay, so take note of that. So on that note, I'm going to get my denominator of the first fraction here. I know will be this to the power 1, but I won't write the power 1. It will be just s squared plus 1. It's simply understood to be there. Okay, then the next one will be your s squared plus 1. You increase the exponent by 1, so it will be squared. The next one, the denominator will be s squared plus 1. You increase the exponent by 1, cube. You can't go beyond cube. In any case, you knew you have 3 fractions. So you've exhausted the denominators of the 3 fractions. Now, because your denominator, okay, is quadratic, remember we said the numerator will always be a degree lower than that of what? The denominator. So if, like I said, okay, we said we will start with constants, which will give us to the power 0. Then we come to the power 1, which is linear. Okay, to the squared, which is quadratic, cube. Okay, so if your denominator is quadratic, your numerator should be linear. And every linear expression, remember we said, is of the form ax plus b. But in what we are doing, you can see that always our letters the constants, we use capital letters. We don't use small letters. So that's the more reason why we have as plus b. If you want to use small letters, you can use. Only that usually we use capital letters. Is that clear? And that's exactly what I've stated here. Where A, B, okay, so you use capital letters. Okay, for the letters that you will introduce. Okay, so the numerator, because your repeated factor is quadratic, the numerators, each of them will be linear. So linear AS plus B, linear CS plus D, linear ES plus what? F. Okay, Prophet Refua, let me see if your network will be better.
Please, can you hear me now?
Yeah, it's a little better.
Power does not affect it.
Come again.
Does it mean that the power does not affect it? Like the power does not make it quadratic or cubic. It's what is in the bracket that we are looking at.
Yes, you are looking at your repeated factor, its nature. It's the repeated factor that is what? Quadratic. So that will tell you, okay, the numerator, okay, expression there, its nature.
Okay.
All
Yes,
right.
please. Thank
Okay, you are welcome. Okay. Okay, can I move on now? Are we all
Yes,
fine?
please.
Okay, great. Okay, please ask question. Remember, I've told you I'm here because of you. So now let's look at our first word example under what? The repeated factors. Okay, because I don't want us to, that's the more reason why. Okay, I have already, instead of writing this, I've typed it there, but you will write it. Okay, so the first word example, write the partial fraction identity. So you underline this, meaning you don't go beyond the identities. Okay, of the following. Okay, so now the first thing that you write is solution. Okay, then your question number A, giving you extract. Now, if you look at what we have here, okay, obviously the first, let's ask ourselves, that first question is very critical, whether this is, okay, proper or improper. Degree of the numerator is 1. What will be the degree of the denominator? Hello, what's the degree of the denominator?
1.
Oh, really? Remember, I told you, okay, you need to expand first, but I gave you a trick, okay, to avoid the expansion. So if you want to, in actual fact, the denominator contains 2 factors, which will be x minus 3, x minus 3. Okay, this one has a degree 1, this one has a degree 1. So if you add, the overall degree will be 2. You get it? Because if you expand this, you get quadratic. You get it? So the degree of the denominator is 2, not 1. Are we fine now?
Yes, please.
Okay, all right. So now what do we do? This is a repeated factor. Okay, obviously now we know that it's proper. Degree of numerator 1, denominator 2, so proper. So once it's proper, we come to the denominator. The denominator here, okay, so the denominator is a linear, okay, which usually is not factorable, but it's repeated. Okay, so on that note, it means I can write the identity straight away. Okay, Prophet Refua.
Mr. Hackman, please. I wanted to ask that. You said the degree of the denominator is 2.
Yes.
But then this also linear.
Come again.
In the previous examples, the x plus 1, we said it was linear. So meaning that the degree will be 1 or
X plus 1.
squared.
S plus 1 squared.
Yes, please. So does it mean in
No,
that one
S plus, did you say S plus 1 all squared?
all squared? Yes.
No,
please.
I did not say the degree is 1. Oh. I didn't say that. Remember, this is where I'm going back. Listen carefully. I said the degree of your repeated factor. Okay, so here, this is your repeated factor. Okay, your repeated factor, what's your repeated factor here?
This x plus 1.
Okay, so what is, so your repeated factor, you said S is S plus 1, not S plus 1 squared. I hope you are with
Yes.
me. So your repeated
Yes.
factor, what is its nature? Is it linear or quadratic?
Linear, the repeated factor.
Yeah, the repeated factor is linear, is that not it? So the nature
Yes.
of your repeated factor will tell you the nature of your numerator.
Yes, I
Or
understand.
numerators. You get it now?
Yes.
Okay, very good. Okay, so
Yes.
if that's the case, then I can move on. But here we were determining the degree of the original rational function. Okay, so the degree here, okay, did I say that? Yeah, the degree of the denominator of the original rational function, or we're determining the proper or improper of the original rational function that you have there. So we said this is proper because degree here is 1, degree here is 2. Because if you expand this, the highest power of your denominator will be what? Will be 2. Okay, so that is cleared. Once that is cleared, we come to the denominator. The denominator, I have repeated factor, but the factor that is repeated is linear. So it means my power of the repeated factor, the number of times that your factor is repeated, will tell me the number of fractions that I'm going to get. And here is the case, you said the power is 2. So how many fractions? Possible fractions? 2. Is that not it? But because my repeated factor is linear, it means each of the fractions, the numerator will be a constant. You get it?
Yes.
Okay, because your repeated factor is linear, okay, the fraction, each of them will be, the numerators will be. So at this point, I can draw my conclusion straight away. I'm matured. So I'll write therefore, because I'll write the identity, because this is not factorable. I'm not going to factorize before I can write the identity. Okay, so now I'll write therefore 2x plus 1 all over, okay, x minus 3, okay, all squared. Remember, will be identical to the 2, you said 2 fractions. Okay, the first fraction, the denominator will give you x minus 3. Okay, that's the first possible factor of this. The second one will be x minus 3 squared. Do you agree?
Yes.
Okay, so because your repeated factor is linear, the numerators will be a constant. So constant A, constant B. Afa? All
Yes,
correct,
please.
my professors. Okay, so now let's look at that of this one as well. Okay, so with this one too, what is the degree of your numerator? Numerator is 2. Is that not it? The degree of the denominator, this is repeated 3 times. So it will be x, okay, 2 minus 3x, 2 minus 3x, 2 minus 3x. So all of them, it will be 1, 1, 1. So the, okay, denominator, its degree will be 2. Do you agree? Do you agree?
Yes, please.
Then it means you don't understand. All right, okay.
Please come again.
You shouldn't agree. Okay, so I intentionally did that. I wanted to see whether you just say yes. Okay, so remember, I've told you before you can get the degree, okay, if it comes in factors, write out the factors in their explicit form, the complete factors, or then it means you have to expand. But I've told you the expansion will not be necessary. So at the normal sequence, it means what the denominator that we have here, its actual factors that we have, there will be 2 minus 3x, okay, multiplying 2 minus 3x, okay, multiplying 2 minus 3x. Do you agree? But instead of writing it this way, it is mature to write it this word cube, to write it this way. Because if you have x times x, okay, I don't think you leave your answer this way. You write it as x squared. All correct. That's the matured way. So
Yes.
once you have this, remember I taught you instead of expanding the whole of this, use each of the factors, get the degree of each of the factors, then add. That will give you the overall degree. So the degree, this is linear degree 1. This is linear degree 1. This is linear degree 1. So if you add, you are going to get what? 3. All correct. So the degree of the denominator is 3, not 2. You get the point now.
Yes.
I guess your understanding is better, so you cannot and you shouldn't, okay, fall victim to, okay, my tricks.
Yes.
Okay, very good. Okay, so at this point, we know this is linear and it's repeated. Because your repeated factor is linear, okay, remember, we said here it's not factorable, so we can also draw the conclusion straight away. So therefore, 4x squared minus x plus 1 all over your 2 minus 3x, okay, all cubed. Okay, I have to clear this because I will need that space. Oops, what is okay? So like I was saying, now let's look at the power. The power is telling us that how many fractions are we going to get? Maximum number of fractions. 3. And because you are going to introduce letters, you can use your identity. So your first fraction, okay, plus your second fraction, then plus your third fraction. Okay, your first fraction will be 2 minus 3x. Do you agree? The denominator. Okay, what will be the denominator of the second fraction?
2 minus 3 all squared.
2 minus 3x, not 3.
X
Okay,
all
all squared. Very good. What will be the third one?
2 minus 3x cube.
Very good. So now your repeated factor, is it linear, quadratic, cubic? Your repeated factor, what is its nature?
Cubic.
Oh no, your repeated factor. Which factor is being repeated? What is the repeated factor in this denominator? Your
2
factor
minus 3x.
your factor is 2 minus 3s and it's repeated 3 times. So this is your repeated factor. 2 minus 3x is what? It's a linear factor. Am I right?
Yes, please.
Okay, so when it is linear, what do you think the numerator should be? A constant, is that not it?
Yes, please.
Okay, so each of them, the numerators will be a constant. So it will be A, B, C. All correct, my professors.
Yes, please.
Okay, very good. Okay, so now if that's the case, then let's move on to the next one. But before we move on to the next one, any questions? Hello, any questions?
No, please.
Okay, you are fine. Your spokesperson says no. So I'm going to continue. Okay, so now let's come to this. You know, the questions as we move from one to the other, a little more bones. So you need to think a little more this time round. Okay, so let's see. What's the degree of the numerator here? What's the degree? 2. Very good. The degree is 2. Very good. Now, okay, you can see that this is a repeated factor. In actual fact, if you are supposed to write, okay, the denominators here in their explicit factors, you know that we are going to get, this is the same as x minus 3 multiplying x minus 3. That is for this one. Then you get what? X plus 1 multiplying x plus 1. So at the normal circumstance, this is what, okay, should have been here. But because we know that every will be this one multiplying itself, okay, will give you twice. Multiplying itself, the power will be 2. So that's the matured way. So if you are using this one to get the degree of this one is 1. This is also 1. This is 1. This is 1. So the overall degree will be, it will be 4. Very good. You add. So it means this is 2 over 4. And 2 over 4, sorry. 2 over 4 is what? Is proper. Am I right? Okay, so once 2 over 4, you know, once it's proper, then it means, okay, you know, your next point, of course, should be the denominator. But the denominator, this time around, you can see that you have 2 factors that are repeated. One of the factors will be x minus 3, and the other factor is s plus 1. True or false?
True.
True. But you can see that each of the factors that you have there, which are repeated, are linear factors. So your first linear factor here has a power of 2. So that tells you that how many fractions will this factor give you? 2. Okay, if you come to this one too, okay, s plus 1, its power is what? 2. So how many fractions, okay, will this give you?
2.
So in all, how many fractions?
4.
4. You get a point.
Yes, sir.
Okay, so if that's the case, then this is the best way to go. Okay, you can write your identities now. So I am going to, because I'm not going to factorize anything or simplify anything. So at that point, I can draw my conclusion. So therefore, 1 minus 2x over, okay, so it's 2x, I didn't complete it, minus s squared all over x minus 3 all squared. Okay, then times what? X plus 1 all squared will be equal to, you said 4 factors. So the first factor plus the second factor plus the third factor, then I'm coming down, plus the fourth factor. Is that clear?
Yes, sir.
Okay, the first factor, the first 2 factors will come from this, okay, linear factor. So it means the denominator, the first one will be x minus 3. The second one will be x minus 3 all squared. All correct?
Yes, sir.
Okay, now the last two will come from this. So what will be the third denominator?
X plus 1.
X plus 1. Very good. And the next one?
X plus 1 all squared.
Very good. Okay, so now remember, because this two fractions that we have here is coming from a linear repeated factor. Okay, its numerator will be what? Will be constant. So a constant A, a constant B. Your second repeated factor is also linear. So the numerators, okay, for each of the fractions generated from that will also be, okay, constant. So C, then D. All correct?
Yes, sir.
Yeah.
Sure. Okay, so any questions before we move on to the next one, the D? If indeed you are following, then okay, we are doing well. We thank God. Okay, so any questions before we move on to the D?
No, please.
Okay, we are fine. So now let's look at that of what? Of the D. Again, this time around is going to be a little technical or a little more difficult than the C, okay, and the previous ones. Okay, so let's see. Always the first question, okay, before you throw away your mouse, the first question will be proper or improper. So we will use the degree. Degree of the numerator.
Two.
2. The degree of the denominator.
4.
4. Very good. Because it will be this one multiplying itself twice. The first factor will give you degree 2. The second factor will also give you degree 2. If you add, you get 4. So proper or improper?
Proper.
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 Okay, very good. So once it's proper, then it means we move on to the, what do you call the denominator? Now, the denominator here, okay, you can see that we have a quadratic repeated. Am I right?
Yes, please.
Okay, now remember we said for quadratic expressions, okay, you know that it's likely to be factorable. Is that not it? So let's check whether this quadratic expression that we have in the denominator is factorable or not. So can I get factors of what? Minus 3. That's when I add, I will get minus 1. When I multiply, I will get minus 3. Factor pair. Hello, my professors. Can I? Remember, I gave you the trick. How do you determine that a quadratic expression is factorable?
B minus 4AC.
What's minus 4ac?
B.
No.
B squared.
B
Minus 4.
squared.
Square minus 4AC.
B squared minus 4ac should be
A perfect square.
a perfect square. So if you are in doubt, you are looking for the factors and you are not getting them, and you want to confirm, use that. But obviously, you cannot get factors of minus 3. That's when you add, you get what? Minus 1, and you multiply, you get minus 3. No. So it means it's a quadratic expression, but it's a non-factorable quadratic expression. Do you agree now?
Yes, please.
Okay. So once it's not factorable, then you are good to go. You can draw your conclusion straight away, meaning you can write the identity straight away. So you come and write therefore, okay, your 3x squared minus x plus 1 all over your x squared minus x minus 3. The whole of that was squared. Okay, now this will be identical to. Now your non-factorable quadratic expression, what is its exponent? 2. Is that not it? So once it's 2, then it means it is repeated how many times?
2 times.
2 times. So remember we said we will use the power here, okay, to determine the number of fractions. So it means the maximum number of fractions that we can get will be will be 2. Is that not it? Okay, so you get your first fraction, then plus your second fraction. All correct.
Yes, sir.
Okay, so your first fraction, what do you think the denominator will be? What will be the denominator?
X squared minus X minus 3.
Very good.
minus
Your
X
repeated
minus
factor. Okay, very good. So S squared, you are doing well. Okay, minus what? X minus 3. That's your first one. And your second one will be this one squared. Okay, so which is the X squared minus X minus 3 all was squared. Okay. All right. So it's like the whole of this is your AX. So X, then X squared. Okay. So now the denominator here is quadratic. Your repeated factor is quadratic. So what do you think the numerators, the natures will be, or the nature will be?
Linear.
Linear. So every linear expression is of the form AX plus B, linear in one variable. So usually we said we are not going to use small letters, so we use capital letters. So it will be AX, okay, plus what? Your B. Okay, and this one ordinarily should have been AS plus B, but A has been used, B has been used. So it means we have to go for C, X plus what? D. All correct.
Yes, please.
Okay, I guess my point is well made.
Yes, sir.
Okay, very good. So now, okay, writing the identities so far, I think so very good. Okay, so let's see the situation that's where we could be what? We could be tricked. Okay, so at this point, I think we'll go for our water break. Okay, but whilst having your water break, when you come back from the water break, this becomes your assignment and it's a class assignment. Okay, we'll mark together, okay, here. So I will give you your water break by 7:05. You should all be back. If you go and you try it, okay, you can try. Okay, but bear in mind that you will submit. So present your solution in a way that it can be submitted. Okay, so welcome back from the water break. Okay, so quickly let's have a look at the solution to the assignments. Okay, this was the class assignment or is the class assignment. Okay, so as usual, okay, the first thing that you write is solution, then you extract. That will be B1. Okay, as for this one, everyone is supposed to get it. Okay, at least. Okay, now you check your denominator. You remember, first of all, check whether it is proper or improper. Degree of the numerator is 1. Degree of the denominator, okay, will be what? 4. Because this will be the same as S squared minus 16 in brackets, then S squared minus 16 in another bracket. So the first one will give you degree 2. The second factor will give you degree 2. So if you add, you end up getting degree 4. So it will be 1/4, which is what? A proper. Once it's proper, remember the next thing is to come to the denominator. Okay, you can see that your denominator has a repeated factor. And that is what? A quadratic factor, S squared minus 16, but it's repeated twice. And here, remember, you cannot straight away go and write the identity. Because remember, I said before you can write the identity, okay, your factor that you have there shouldn't be factorable, none of them. But obviously, we can see that there's a quadratic expression that is factorable. So we have S squared minus 16. Okay, this is a square of a quantity X. Then minus, so 16. Okay, then 16 is 4 squared. So I should know that I'm dealing with difference of 2 squares, which I know how to factorize. So if you come and write the identity symbol here, I'll come to the penalty. You only write the identity symbol when you are introducing your letters. But what you have here is not identical to this, but it's equal to this in a different form. The identity will come in. I saw that some of you introduced the identity at this very first step. So now it means you cannot write the identity. You have to go and factorize. And as you are factorizing, you have to be very careful. So the factorization is for what you have in brackets, which will give you X. In actual fact, what you have there is S squared minus 4 squared. So that will give you X plus 4 Okay, then x minus 4. That will be the factorization of what you have there. But remember, it's the whole of what you have here, okay, squared. And from indices, if you have a, b, okay, all to the power m, we know that this is equal to a to the power m times b to the power m. So it means what I have here, my a is the whole of this and my b is the whole of this. So my denominator in actual fact will give me x plus 4 all squared then into x minus 4 all squared. So that will be what you have there. So the factorization is this. Okay, so this becomes the first step, m1, where you factorize this and you put this in brackets. But you can see that we don't write the identity when we have a square bracket. So it means you have to remove the square bracket. And in removing the square bracket, it will be this one squared, which is what you have here, then this one squared. Please take note, if you come and write plus here, you are wrong. It will be m0, okay, a0, because this cannot be plus. You are factorizing. So I saw someone with a plus there. So at that step, give yourself m0. Okay, going forward, marking becomes very easy, a0. So you will only get this and this, provided you have this one there. So at this point, you can see that this takes us to one of the situations that we encountered. So you have a repeated factor, linear, repeated linear twice. So in this case, remember, we can write what our identity. So at that point, you can have your conclusion drawn. So therefore, your 2s, what you are given here, will be identical to, so this is where you introduce your identity, because that's where you are introducing your letters, and that will give you a over s plus 4. In actual fact, it will be s plus 4. Okay, that is coming from this. Then the second factor will give you s plus 4, the second fraction, all squared. So you know, as for here, the explanation, I think you get it. This factor will give you 2 fractions. This will also give you 2, so 4 fractions. So all of them are linear factors. So it means the numerators for each of them will be constants. So you write your a, b, c, and that will be a, okay, 2. So in all, what you have here will give us 5 marks. Okay, so whatever that you had, you've marked. Okay, write the total. If you had 5 over 5, write 5 over 5. If you had 2 over 5, 1 over 5, please write it and capture. Okay, so this will be it for the solution to the class exercise. Okay, so now let's go and look at, okay, the real, okay, deal, okay, which is the resolution, okay, of rational functions into partial fractions. Okay, so now I'm going to read. We are going to look at, well, resolving rational functions into partial fractions. Okay, and I've told you getting the identity is key. Okay, and going forward, you will know. So I read, partial fractions are the fractions used for the decomposition of rational functions or expressions. Remember, okay, functions are expressions with special names, basically. When a rational function is split into a sum of 2 or more rational functions, then each part is called a partial fraction. And indirectly, I've been using this, so I think you are familiar. The process is called resolution or decomposition into partial fractions. So the process of splitting, okay, your rational function into the sum of 2 or more rational functions is what we call resolution or decomposition into partial fraction. Is my point well made? Hello, is my point well made, my professors? I hope the explanation to the introduction is clear.
Yes, sir.
Okay, very good. So now let's see how, okay, we resolve, okay, rational functions into partial fractions. So to resolve or decompose a rational function into partial fractions, okay, we follow these steps. Okay, 1, the first step, write the partial fraction identity. of the given rational function. So you can see that the first step is to write the partial fraction identity. So if you don't know how to write the partial fraction identity, it means the rest of the steps, okay, done. You can't, okay, deal with it, because the partial fraction identity is key and this is the first step. Okay, all right. Then after that, what do you do? Express the partial fraction side, okay, which will always be the right-hand side, usually, as a single fraction. So when you resolve, okay, or let me say, when you write the partial fraction identity of the given rational function, and you know, whenever you are writing the partial fraction identity of the rational function, you are going to get at least two fractions, so which will be more than a fraction. Okay, so the side that you have more than a fraction, you now come and write it as a single fraction. So that it's like, okay, on each side you have single fractions. Okay, and the single fractions that you have on each side, they will automatically have the same denominators. So you will have a proportion or an equation formed with connecting two fractions, two ratios, okay, where the denominators are the same. So if the denominators are the same, it becomes obvious that the numerators must be the same. So you equate the numerators. Now, when you equate the numerator, this is what we are going to do. Okay, remember, whenever you are writing the partial fraction identity, you will introduce letters. Okay, so you now go and find the values of the letters involved and go and substitute. However, how do we find the values? So we said find the values of the introduced letters A, B, C, etc. by either, okay, so this is how you find the values. A, using the cover up or the elimination method. Using the cover up or the elimination method, i.e., substituting 0 in the factor variable. Substituting 0 in the factor variable. Don't worry, if it's not clear to you, I will throw more light on that, okay, going forward when we are dealing with the actuals. Then B, using, okay, comparing coefficients method, or using, okay, the method of comparing coefficients, i.e., equating corresponding coefficient. We know how to do that from what polynomial identities. Then finally, what do you do? When you find the values, you have to go and substitute the values. So finally, substitute the values of the A, B, C, etc. into the partial fraction identity. And whatever that you get there now becomes the resolution or the resolved version of the rational function into partial fraction. As simple as that. Okay, so quickly, let's go and look at the following, okay, examples and how best we can subject that through, okay, the steps that I just walked you through. Okay, so are we good to go, my professors?
Yes.
Great. So
Yes,
let's look
sir.
at the first worked example. Okay, so worked example 1. Resolve the following into partial fractions. So here we are resolving into partial fractions. Okay, we are not writing the identity. So we will not end at the identity. Take notes. Okay, so at this point, remember, we said before you can resolve, the very first step is to write the partial fraction identity. And in writing the partial fraction identity, we ask ourselves a major question. The first major question that we ask ourselves is, okay, the rational function that we are writing its identity, is it proper or improper? So let's check. The degree of the numerator here is what? Is 0. The degree of the denominator is what? What's the degree of the denominator?
2.
2. So proper or improper? Obviously proper. So
Proper.
once it's proper, okay, we can straight away move to the denominator. Okay, so our concentration next should be on the denominator after realizing that it is proper. Okay, so denominator, okay, we have linear factors. Okay, and obviously I've told you that usually when you have linear factors, okay, none of them will be factorable. Okay, so here you have distinct linear factors. Okay, so once you have distinct linear factors, each factor will have a fraction. Okay, so it means in all, if I write this, the identity of this, the partial fraction identity of this, how many fractions am I going to encounter? How many? 2.
2.
Okay, 1 for each of the factors that you have there. And take note, I'm writing the identity. Okay, the identity is only a means to an end. So here I cannot write therefore the identity is. I will only conclude when I find the unknowns, then I substitute and get my partial fraction. So I will come and write my identity. That's my next step. So this is identical to, first fraction, my denominator will be x plus 3. Okay, plus my second fraction, the denominator will be x minus 3. All correct?
Yes.
Okay, first fraction, the denominator is linear. So the numerator will be what? My professor,
Constant.
a constant,
Constant.
so A. Okay, linear, so again constant, but we can't use A, we use B. So that was the first step. The second step, we said, let's go back. But I can say it anyway, but I just want us to go back. The second step, we said we should write this side where you have more than a fraction as a single fraction. So let's go and verify. So express the partial fraction side, as a single fraction. Am I right? So this is the partial fraction side. So we are going to write this as a single fraction. So please take note, immediately you write your identity. After that, the rest will be equal to. So this will be equal to, if you are writing this side as a single fraction, what will be our LCM? It will be this one times this, am I right? Okay, so your LCM will be x plus 3, times x minus 3. All correct? My professors, are you with me? Okay,
Yes,
very,
sir.
very good. Okay, now, you can see that the single fraction, the denominator, which is the LCM, is known, but we don't know the numerator. So how do you get the numerator? We will ask ourselves the number of times s plus 3 will go into our denominator. And you can see that the s plus 3 will cancel the s plus 3. So you end up getting x minus 3 by times a. So it will be a, times x minus 3. Then plus the number of times this will go into this. The x minus 3 will cancel. So I'll be left with s plus 3 times b. So that will give you b into x plus 3. Then you extend this. Point well made, my professors. Who wants me to come again?
Sir, please, can you come again?
Okay, all right. So this one, you can see that assuming I give you 1 over, x, or let me even use x plus 1. Then plus 1 over x. What will be your LCM? If I ask you to write this as a single fraction. Prof. Adam, what will be your LCM?
Sir, please. X plus 1.
Okay, that's your LCM.
Yes, sir.
No. S plus 1, because this is not a factor of this, you can't take this as what? Your LCM. Assuming maybe, let me come from 1 over 2 plus 1 over 3. What will be your LCM?
6.
How did you get the 6? By multiplying this and this, is that not it?
Yes, please.
So because this is not a factor of this and this is not a factor of this, you can't write one of them as what? If you had 1 over 2 plus 1 over 4, what will be your LCM?
4.
4. Because this is a factor of this then becomes the LCM. You get a point?
Yes, sir.
But when you realize that none of them, is a factor of each other, then what do? You multiply. So that will give you the 6. However, is s plus 3 a factor of s minus 3?
No, please.
Is s minus 3 a factor of s plus 3?
No, sir.
So it means the LCM will be the product of the two. You get the point?
Yes, sir.
Okay, so that's what you have here. And when you were dealing with this, what would you have done if this is the LCM? You ask yourself the number of times 2 will go into 6, which is 6 over 2. And that will give you 3, then you come and multiply it by this. Is that not it?
Yes, sir.
You come and do same here. So it's the same thing. Okay, so don't get it twisted. It's the same thing. You are asking yourself, so you now have s plus 3 into x minus 3. If you want to know the number of times this goes into that, then divide by s plus 3. So the s plus 3 will cancel this. So you'll be left with s minus 3. Then you come and multiply it by a. But because there's a binomial and the a is multiplying, you put the binomial in brackets. The same explanation for this side. Is it correct now?
Yes, please.
Great. All right. Okay. So this is what I want. If you have issues, okay, please take note. The class size is small. Okay. And this also, Mr. Ackman, I have, okay, a big heart for all questions. Okay. So please make sure you do ask questions. You don't leave the same. All right. So now that, okay, the explanation is clear, I guess we can move on. So now this is what we are going to do. We are moving on to the next step. And remember we said, okay, now we are trying to say that this fraction here is equal to this fraction. Do you agree?
Yes.
Okay, so the two fractions, can't you see that the denominators are the same?
Yes.
And remember, I told
Yes,
you that if
please.
you have A over B, okay, is equal to, okay, C over B. Okay, what will you write? This implies that
A is equals to C.
A is equal to C.
Yes.
Perfect. Okay, somebody will say that cross multiply. You cross multiply, you come and divide by B. You end up getting the same thing. So once the denominators are the same, then I can write, this implies that my numerator should be the same. So 6 should be equal to A into x minus 3, then plus B into what? Okay, x plus 2. Sorry, x plus 3. Remember we said just equate the numerators. That's supposed to be your next step. Okay, so equate the numerators. Can you see that? After writing that side as a single fraction, the next step is to equate the numerators. All correct, my professors?
Yes, sir.
Okay, so now our core work is to look for the values of A and B. Okay, if you don't know the values of A and B, then you can only end at the partial fraction identity. However, we are looking at what just the actual partial fraction. So we need to know the actual value for A and the actual value for what? For B. Then we go and substitute. So in this case, we are going to set up out to look for the values of A and B. And we said we have two methods. One that we call the cover up method, okay, and the other one that we call the method of comparing coefficients or comparing coefficients method. Okay, so first of all, I am going to walk you through the cover up method. Then we'll look at what the method of comparing coefficients, okay, as our alternative method. Okay, so the cover up method, this is what you do. Remember, we said there is something here that I said I would throw a little more light on. Substituting 0 in the factor variable. Substituting 0 in the factor variable. So let's come here. I will show you what we mean by the factor variable here. So the factor variable is this. Okay, the factor, so meaning the factor containing a variable. If you take this, A is a factor and S minus 3 is a factor. Am I right? So let me explain it from this point. A is a factor, S minus 3 is a factor, B is a factor, S plus 3 is a factor. So this is your factor variable because this is a constant. Okay, this is also a constant. However, this is a factor variable. So you have two factor variables. All correct. All correct, my professors. Okay, so now this is what we are going to do. With your factor variable, okay, I can cover up the B. If I cover up the B, then it means I want to eliminate the B. Okay, if I want to eliminate the B, then this is what you do. You carry out a substitution for X. Okay, so that, okay, the whole of this will be 0. Okay, and if the whole of this is 0, it will be B times 0, so B will go. Okay, A will be standing. Then you can find the value for what A. And this is how you do. If you want to get what's substitution for x that will give you this to be 0, just equate this one to 0 and solve. So it means x will be equal to -3. You get the point? So if x is equal to -3, this factor here will give you 0. However, this one will not. So I'm going to write this is what you write. If in some books you see when, but from today, if you've been taught and you've been using when, don't use when, use if. In math, what if can do, when can do, if can do and do it better, save you time. So if x is equal to the first value of x, we are going to look for -3. This is what we have. I'm going to come down, but usually I'll tell students, not to come down if we can go there, just to save. So I'm going to substitute. So I will get 6, is equal to A into, we said x is -3, so it will be -3 minus 3. Then plus B into -3 plus 3. All correct. Hello, is my point well made so far? This is the first example, so make sure you get it from the beginning up to the end. Are we all following?
Yes, sir.
Okay, so if I come down, I can write implication or ignore because now I'm dealing with an equation. I will use implication. This implies that 6 will be equal to, this is -3 minus 3. What would that give us?
-6.
-6. As you mature, we'll write this one straight away as -6a. Because there's the first example, you know what I do. I try to break it down for you to appreciate the concept. And as you mature, I will take out the one that you can take out. Then plus, this will give you b into -3 plus 3. 0. So in effect, we are going to get 6 is equal to -6a. The plus 0, we don't write it. We are looking for a. We can solve for a now. So -6, a, over -6 is equal to 6 over -6. So it means a will be equal to -1. All correct. So a, you can't draw your conclusion with a because the question didn't ask us to find a directly. A is a means to an end. So the best you can do is implies. Not therefore. You move on. So then if I want to find the value of B, I can cover up the A. So if I want to cover up the A, then it means I want to eliminate what the A. So on that note, I equate this one to 0 and solve. So that will give me S to be equal to 3. I'm doing that mentally. If you are not mature, then you come and do that. X minus 3 is equal to 0. So x will be equal to 3. So meaning, if you want A to go, x must be equal to. So at that point, I'll write if x is equal to +3, comma, I'm going to get 6 is equal to, I will substitute that into this. So I will get A into what? Into 3 minus 3, then plus B into 3 plus 3. Am I right? So this implies that, 6 will be equal to A into 0, plus B into 6. Am I right? Which gives us 6 is equal to A times 0 is 0. You don't write it. B times 6 is 6B. So you write it again before you divide. So I'm going to get what 6B is equal to, you can keep the 6B here. The fact that I've written here doesn't mean I've moved. Remember, if A is equal to B, B is equal to A. Just for convenience that I've written this one first. So over 6 over 6. So we are going to get B also to be equal to 1. So at this point that you know A and B, remember the last step. Go and substitute that one into your identity. So substitute the values of your found letters that you introduce, into the partial fraction identity. So we are going to do that. So where is our partial fraction identities here? But because you know the values of A and B, this is no longer the identity. It's at the actual partial fraction. So you write therefore, what you were asked to resolve 6 over, okay, x plus 3 as one factor, okay, x minus 3 as the other factor, will be equal to your A. A gave us negative. So I'm going to write it, but I'll tell you what to do as you mature. So I'm substituting directly. So that will give me minus A over, oh, sorry, minus 1. I know. Why did I write minus A? Interesting. So minus 1, let me write it. Okay, well, minus 1, okay, over your s plus 3. I'm substituting. Then plus, what is your b? B gave us 1, so 1 over, okay, x minus 3. But you know, I've told you in maths, if you have a positive term and a negative term, you start with a positive term first. So as you mature, when you are carrying out your substitution, check which one is positive, which one is negative, and write the positive. So it means as you mature, you can do away with this step and come straight away to this. Okay, which will give you, I'll write a positive first. So 1 over x minus 3. Then this one, the negative will come here. Then it will be 1 over x plus 3. All correct, my professors?
Yes, sir.
Sure. Is everyone okay, my professors? Hello, my professor. Is everyone okay?
Yes, sir.
Yes.
Okay, very good. Okay, so on that note, okay, this will be it for the cover up method. Let's look at the alternative method. The alternative method, you start the same way. Okay, when you equate, remember we said for all of them. Okay, so let's go back to the steps and see. Okay, so for, okay, where you have the alternative, okay, it will come in when you are finding the values of the unknowns, and that will be after you've, okay, equated the numerators. Okay, so it means step 1, step 2, step 3 will be there before you come and use the second method. Is that clear?
Please.
Okay, so now this is what I'm going to do. Okay, so let me see if I can go back to, so that we don't waste time. I want to do something. So, all right, so let me, okay, pause recording. I want to do something quickly. Okay, so just as I was saying, there's the alternative method. The alternative method, you go through the step 1, step 2, then step 3. So you have all your steps. However, when you get here, that's where you have an alternative approach in finding your A and B. Okay, so this time around, we are not going to use the cover up, but we are going to use the method of comparing coefficients. So indirectly, what we have here is what? A polynomial identity. And remember, before you can compare, okay, because that's the method that we are going to use, comparing coefficients. Before you can compare the coefficients, make sure there are no brackets. Okay, I mean, there is no x in your brackets. Okay, then any bracket that you have there should be only letters, not your variable. So it means this calls for expansion, okay, on this side. So I'm going to write more or less 6, okay, will be equal to our expanders, which will give me ax minus 3a, then plus 3, bx, okay, plus 3b. Okay, after expansion, remember, we should always, okay, combine like terms. So this and this are alike. So I will get a plus b in one bracket, so then what? X. Then your constant there will be, I want to write, okay, it doesn't really matter, to be minus 3a plus 3b. I cannot combine them. Okay, take notes. I have to write it this way because, okay, so now what do? We compare coefficients. So comparing, I hope you are following my professors.
Yes.
Okay, so you see why polynomial is closely linked to, okay, the partial fraction. So now that our polynomial identity is strong, so comparing coefficients will come to the here, the highest it will be x to the power 1. So x to the power 1, which is the x. Okay, you have a plus b here. Okay, should be equal to, do you have any s term here?
No, please.
So it means its coefficient is what?
0.
0. So you call this equation 1. Okay, then x to the power 0, which is your constant. Your constant here is 6, but here your constant is minus 3a plus 3b. So I'm going to write that minus 3a, okay, plus 3b should be equal to positive 6. But unfortunately, I will not label it. Oops. Okay, so let me write my 6 well. It's not appearing. Okay, so unfortunately, okay, I'm not going to label it, okay, because I know I can reduce the equation. So I'm going to divide by negative 3 because I want my leading one to be positive. So this by negative 3 will give me a. Okay, this by negative 3 will give me, oops. Okay, so sorry. I clicked on, let me, okay, stop recording anyway. I'm coming. Oops. Okay, all right, so let's continue. So that will give us minus 3, minus b is equal to 2. Do you agree? My professor, do you agree? Hello, my professors, do you
Yes,
agree?
sir.
Very
Yes.
good. Okay, so on that note, we are going to solve these two equations simultaneously. And you can see that we can add to eliminate what? The b. You can subtract to eliminate the a. So any of them that you want to eliminate, you eliminate. Okay, Prof. Refua. Very good. I hope you have seen. Very good. It's okay. It's okay. Okay, it's okay. I wanted us to finish, then I will draw your attention and see if you divided by negative, so this should be negative 2. So it means you are not following. Okay, so please take note. You have to be very careful. Some of these common errors that students do that I'm drawing your attention to. Okay, you are lucky your attention is being drawn to. So make sure you, okay, do the right thing. Other than that, you are doomed from here. So at this point, I'm going to eliminate b. So it will be equation 1 plus equation 2. Okay, comma. So I add this and this, I'll get 2a. Okay, this and this will go. That's my intention. This and this will give me is equal to minus 2 because it will be 0 plus minus 2, which is this. So I write it again before I divide. I hope you are following my professors. So a will be equal to negative 1. Then again, once I know a is equal to negative 1, I can substitute a to find my b. So I'll call this equation 3. Then go and write equation 3 into any of the two equations. I will go for 1. So into, okay, equation 1, comma, and that will give me a, which is negative 1, okay, plus b is equal to 0. So I will get b to be equal to negative 1. You move it there 1. So now, therefore, okay, my 6 over, okay, x plus 3 into x minus 3, okay, resolves into, okay, my a. So this time around, no, my a is negative, my b is positive. So I'll start with the b first. So b is 1 over, okay, x minus 3, then minus my 1 over x, okay, plus 3. All correct, my professors?
Yes.
Is my point well made, my professors?
Yes, please.
Okay, very good. At this point, okay, we are going to look at one more question. Okay, one more question under this. At least then I will know that you are fully insured to, okay, try the question that we have here. So quickly, let's move on to the next question, which is question B. Okay, so question B, this is what we have. So let's quickly look at that of the B. All right, so solution, again, proper, degree 1 numerator, degree 2 denominator. So a proper rational function. So we can write the identity. This is not factorable. So you can write the identity straight away. So this is identical to, okay, a over x plus 1, okay, plus b over x minus 2. Okay, so at this point, single fraction all the way. So equal to your single fraction. Remember, At the point where you introduce your letters, that's where the identity symbol will be. After that, equal to all the way. So this will give us x plus 1, okay, then x minus 2 as our LCM. Okay, this goes here, x minus 2 times, then times a. So it will be a into x minus 2. Then plus, this will be b into s plus 1. Okay. All right. So now what do? We are going to use, okay, now that the denominators are the same, you equate the numerators. So this implies that my numerator, okay, 3x should be equal to the numerator here, a into x minus 2 plus b into, okay, x plus 1. Point well made, my professors.
Oh, please.
Yes.
Did I hear no?
Yes, sir.
From where? Adam, is that you?
Yes, sir.
No, as for this one, I'm not going to explain again how you got this. I'm not, because I explained the other one. You said you got it. So go and use the concept there to get it here. You get it? Okay, so now I said this will go into this. If you want to know the number of, once it's going into this, you have it here, it will cancel. It will be this times your A. This will go into this will cancel. So I know if you want to know the number of times this will go into this one divided by this. So the x minus 2 and the s minus 2 will cancel. You'll be left with this, then times that. Okay, so as simple as that. So at this point, you equate. Okay, we are going to use the cover up method. Okay, so that's what I'm going to use. And please, it is advisable to use the cover up method when you realize that all your factors, okay, are linear. Okay, when you see that, it is always convenient to use the cover up method. Okay, so no matter how much you are in love with the comparing coefficient method, use it when your factors are all linear. So at this point, I can, forgive me, I can cover up B. If I want to cover up B and find A first, it doesn't really matter which one you find first. Okay, let me find the B first here for you to know. So if I want to find the B, then I have to cover up the A. Hello.
Mr.
Yes.
It doesn't mean if you don't use the cover method.
No, I won't.
It doesn't mean that if you don't use the cover up method, you'll be marked wrong.
No. That's not I say. When I say convenience and ideal, okay, it means that's the one that will save you time, okay, and space. Basically. So when we know that the ideal method is, elective man, now we are giving constraints. So because we know that the ideal method is the cover up method, the space that you provide there usually will be for the cover up method. So if you go and use any other and, okay, your space is exhausted and you still have, then you will now come and rule a line and continue here. You get it?
Yes.
So always go for, because exams you are working against time. So always go for the convenient method. And convenient, okay, more or less ideal method. Okay,
Yes.
it's when maybe, let me use ideal method. It's when maybe the ideal method, you are not too familiar with that. And you want to use your convenient method, you use. Your convenience will be the one that will protect your marks. Okay, the one that you are comfortable with. So at this point, I want to cover up the A. So I will equate this one to 0 and solve. So x will be equal to 2. So I'll come and write if x is equal to 2, comma, you can say that this time around x is here. So it will be 3 into 2. Okay, it's equal to A into 2 minus 2. Okay, then plus B into what? 2 plus 1. So in this case, this time around, like I said, I'll handle it maturely. This time, this will give you 6. Okay, it's equal to, this will give you 0. So don't write it because your intention was to eliminate that. This will give you 3. You can add this 3 times B. So that will give you 3B straight away. Is my point well made?
Yes, sir.
Okay, you write it again before you divide. But I want to write the 3B first. Okay, so over 3 over 3. So your B here will be equal to 2. Okay, now again, you go and cover up this time around B to find your A. So if I cover up the B, If I want this to go, s must be
Yeah.
equal to 1. So if s is equal to negative 1, okay, I will get 3 into negative 1. Okay, should be equal to, okay, I'm substituting that here. So it will be a into negative 1 minus 2. Then plus b into what? Negative 1 plus 1. Okay, so this implies that, okay, 3 times negative 1, I'll get negative 3, will be equal to negative 3 times a, so negative 3a. Okay, this will give me 0. 0 times b, so that will go. So I'll end up getting negative 3a is equal to negative 3 over negative 3 over negative 3. So it means a will be equal to 1. So at this point, I know the values of my a and b. I draw my conclusion. So fortunately for me, this time around, a is positive, b is positive. So it's better I start with a because a is positive. So I'm going to, okay, I can start with a. The first one, a is positive. So any of them will go, but don't change the order, okay, when the first one is positive. So that gives us what? 3x over, okay, our x plus 1, okay, into, okay, x minus 2, okay, will be equal to, not identical to. Now you know the values. So a gave us what? 1 over its denominator. What's the denominator of a? S plus 1. Okay, plus b gave us what? 2. So 2 over its denominator. What is the denominator? X minus 2. Okay, as simple as that, we are done. All correct.
Yes, sir.
Okay, very good. So now, before we bring down the curtains, okay, to today's lesson, okay, I'm going to guide you. With this one, this is what you do. Okay, this is a quadratic denominator which could be factorable. So if it's factorable, then it means you cannot write the identity. You come and write equal to. Take this one, go and factorize as your rough work and come and get your exact linear denominators or factors. Then now you can write the identity and proceed. Is my point well made, or you think we should do one?
Yes, sir.
Which is it? We should do one, or my point is well made?
We should do one.
Okay, so we are going to do the C. Okay, I will do it up to a point just to guide you. Okay, this one, the alternative method will be the method of comparing coefficients, which I said, okay, I will skip because of time. Okay, so let's move on. We've exceeded. So let's deal with this one. I will do it up to a point. So given this, okay, I cannot write the identity straight away because this is factorable. So that will give me, this is equal to, I will take this one, I'll go and factorize. And here I can factorize straight away because my leading coefficient is 1. Okay, so at that point, I'll write 8x minus 28 all over. Okay, now I know I will get my factors x, okay, in bracket, another bracket x. Immediately I get my factor pair, I'm done. So factor pair of 8, which when you add, you get minus 6. When you multiply, you get what? 8. Give me the factor pair. If you can do this straight away, you can go and do your rough work for the factorization.
Minus 4 minus 2.
Minus 4 minus 2. Okay, so I will write here minus 2 minus 4. You are done with the factorization. If you go through the factorization, okay, process for the grouping, you end up getting the same thing. Okay, so this one is a special situation for the leading coefficient being 1. So at this point, I can write the identity. So this is identical to, this linear will give me a, okay, over x minus 2 as its fraction. The other linear will give me b over x minus 4. All correct. So at this point, you come and write this as a single fraction. And I'm going to do this because of Prof. Adam. Okay, so at this point, your LCM will be this one times this. So x minus 2, okay, into x minus 4. And if you are in doubt, please, okay, always your LCM will be the same as what you have here. So LCM, your factorized denominator. Okay, so now x minus 2 will go into your denominator how many times? So it will be the whole of this one divided by x minus 2. The x minus 2 will cancel. In any case, when you had the 1 over 2, okay, plus the 1 over, okay, 3, and you had 6, okay, then know that the number of times this will go into this will be the other one. The number of times this will go into this will be this one. So it's the same thing. The number of times this will go into the whole of this will be this one. So times A. So it will be this one. So it will be A times. Prof. Adam, do you get it?
Yes, please.
Then plus the number of times this will go into the LCM will be this because you multiply it by this. So that will give us B, okay, times what? X minus what? 2. So at this point, you come and equate. So this implies that 8x minus 28, okay, will be equal to A into x minus 4, okay, plus B into what? X minus 2. So here, if you want to cover up B, it will be if x is equal to positive 2, comma, you come and substitute 2 here, 2, okay, here. So that will give you 8 into 2 minus 28 is equal to A into 2 minus 4 plus B into 2 minus 2. So which in effect will give you, this will give you 8 times 2, which is 16. So this implies that 16 minus 28 will be equal to, this will give you 2 minus 4 minus 2. So I'm going to get minus 2A. Okay, then this will give me 0. I won't write it. Come and simplify the size. Solve for your A. Then again, you come and equate this one to 0 and solve for it. So x will be equal to 4. So you substitute 4, and that will help you find your B. You get the point? Is my point well made?
Yes, sir.
Okay, all right. So on that note, this will be it, okay, for today. Okay, so any questions before we finally bring the curtains down to today's lesson? On today's lesson. You are all fine. Okay, so I will send your assignment pretty soon, and that will be this one. Okay, take notes. We couldn't get to where I wanted us to get to, okay, before your assignments will come. Okay, so don't worry. I will give you assignment pretty soon. Okay, so this will be your assignment. Okay, I will send it to you pretty soon. Thank you very much for making the class, okay, a success. Okay, God bless us all.